good, hopefully. Just let me know if it starts acting up. Not that I'm able to do anything about that, but still is a good thing. So, well, let's move the webcam down. There we go. Okay. So last time we talked about the Wittig reaction, right? And I hear one of y'all got yelled at for calling it Wittig. Told you. We looked at how you can take an aldehyde or ketone. Again, doesn't really matter which one you're using. You put it with a phosphorus ylide, which we can sometimes write as... I better make this obvious. Okay. You put that with phosphorus ylide, and you end up getting out an alkene, right? Substituting exactly where that oxygen is. Generally, you will get the Z-alkene, the cis-alkene out of this. Whichever one that happens to be, if you're just using a standard Wittig reagent. If you're using one that has an electron withdrawing group in it, called a stabilized ylide, you'll get the E predominantly. So, for example, I'm going to actually use some with carbons this time. What are you trying to eat there, mister? There's nothing there. Okay, if we go ahead and do this, what shall we put on? How about a nitrile? And a T-butyl group. Why not? So, notice because we have an electron withdrawing group, this stabilizes the ylide, right? Because the ylide is really a C minus, right? It's got a negative charge on the carbon, so having a nitrile there allows it somewhere for it to resonate to. So any sort of electron withdrawing thing, if you've got by resonance or if it's by induction, that's going to give you your E1 predominantly. So if we go ahead and do this, notice we've got the ethyl group that's going to be on the bottom side here. The top side, we're going to get our T-butyl group, which will be on the opposite side because we're going to get the E-alkene here. And we're going to have, what is this, the nitrile. So, I mean, technically this is a Z-alkene, if we wanted to be very careful about our stereochemistry. Really, though, it's about the relationship of putting the bulky things next to each other. So it's generally that does fall in line with E and Z, but really what we're looking at is the bulky things being far from each other. Generally, that is called E, a trans relationship, but technically the nitrile has a higher priority, just because it's got the heteroatom there. So that's, I mean, technically this is a Z-alkene, but it's still got the bulkier groups far from each other. So perhaps this was a bad example. But that's the idea. So we're looking at making the trans alkene here in terms of steric stuff. Because that's going to be just favorable thermodynamically speaking. Usually with these stabilized ones, we're looking at a thermodynamic product rather than a kinetic one. Then the kinetic one, we usually do get the Z in terms of our steric groups. So this is technically Z, but sterically it's E, if I can say that. I'll just say that. Do y'all see what I mean by that? Technically, this is a Z-alkene in terms of E and Z priority naming things, where we look at atomic number. But in terms of like sterics, if we look at steric contribution to this, it's E, right, where they're trans to each other. So, bad example, I suppose. But that's what we're looking at here. So if you have something that is going to stabilize your ylid, meaning you have an electron withdrawing group on it, you're going to end up getting your bulky groups trans to each other. And typically that's going to be an E alkene, but naming-wise, this one is still Z. Although sterically, it's E. All right, let's see. What else can we do? Special cases. We have the Horner, Wadsworth, Emmons. I might have totally spelled these all wrong. Reagent. HWE. Horner, Wadsworth, Emmons. That's an Horner. Again, I don't really care if you know the names, but I guess Chalmers does. HWE. This is a special case of a type of Wittig reagent. We're going to use an ester. So there's our negative charge on this. So actually that can just be another on this. So this one, the Horner Wadsworth Emmons is special because it's always going to be stabilized, right? Because you have the ester that's on it. So you always have this ester that's on the right side here, whatever that could be. It could be an ethyl ester, methyl ester. That R group typically is one of those two. Usually it's methyl or ethyl for the R group. So it's stabilizing our ylid because it gives it a place to resonate, right? So it's always got this this stability here. And when we use this as a reagent, it's going to react much the same way. So remember, this negative charge is kind of held as a double bond to the phosphorus, kind of. But typically we do draw this as a double bond, but it just has that ester there. And instead of using phenyl groups, we're using oxygen-based groups instead. This is much the same. If you take your aldehyde or ketone and use one of your HWE reagents, we'll use this one, and we'll say it's a methyl ester. If we do this, the same thing is going to happen. We're going to end up replacing our oxygen. Everything that's kind of on this side is going to replace the O in your ketone. This time it is a ketone, so I can say that. Okay, so everything there is going to replace your oxygen, and in this case, again, you're always going to get the E alkene. And this time I've made it obvious, so we don't have any other substituents here. So it's both sterically and technically an E alkene because we have both our highest priority groups and our bulkiest groups trans to each other. So this is the E alkene here. And now we have this ester group on it. So it's just the special case of Wittig where you use an ester as your electron withdrawing group. And technically you'll use a slightly different phosphine. It's okay, whichever one you like. So it's just a special case of this where you use an ester as your electron withdrawing group. And again, you're going to get the E alkene over the Z alkene here. All right.
Is this just to get an ester onto something?
Yeah, so I mean, it's really the same thing. Here we use a nitrile. Here we use an ester. But because these people have all done this and got their Nobel Prizes or whatever, I don't know if these people did. Wittig did. I don't know about these people, but this is such a common reagent that it has apparently got its own special name. So because it's just so commonly used, it works really well. These reactions work very efficiently, and you do get a overwhelming majority of E alkene versus Z alkene. So anytime these scientists come up with improvements to name reactions, they'll usually get their name on it as well. So it's just a modified Wittig reaction that uses an ester, and it's a little bit safer, I suppose, because this with the these ethoxys instead of the triphenylphosphine, a little bit safer. So it's a good thing. But yeah, it does exactly the same thing, except you're using an ester as your electron withdrawing group. Nothing different. Mechanism exactly the same. You make the box, and then you close the box down. All right, let's look at how to make these things, by the way. So, making Wittig reagents is pretty easy. I say that, but it has to be done oxygen-free, and in reality, it's actually pretty tough. On paper, though, it's really easy. So you'll take an alkyl halide, and you'll give it the triphenylphosphine, and then a strong base. Typically, here you use butyl lithium as your base. Nice strong base here, and you'll end up with your Wittig reagent. So for example, let's say you want to put just CH2 on. Now we'll be a little bit better than that. So how about we do this? So here's your alkyl halide. Say you want to put 3 carbons onto your Wittig. How this is going to work, your triphenylphosphine comes in here. It's got a lone pair. I'm going to use light blue for my reaction arrows as always. Comes in, kicks out the bromine. You've got your bromine, I guess, just kind of chilling out because it's got a positive thing now. Your base comes in. Again, usually this is butyl lithium, so very strong base. It's a carbon ion. Comes in, plucks off the proton. And you can draw this either way. You could draw it going to make the double bond, or you can just draw it going onto your carbon. I'm going to draw it going onto the carbon because I feel like it. You end up making butane. And your lithium bromide goes away. And we end up with our reagent. So remember, again, this is the same thing resonance-wise as this. So that's how you'll make a Wittig reagent, is you'll just use some alkyl halide. You will use your triphenylphosphine, or if you want to make a HWE reagent, you would use the ethoxy version, not the phenols. Then your base comes in, plucks off the proton, and you'll make either one of these. Either you'll leave your lone pair on the carbon like that, as the ylid form, or you can draw it kind of neatly as the alkene form. Or not alkene, but I don't even know what we'd call that. Double bond to phosphorus. Whichever way is fine. So both of these, remember, resonance, we're good. So you'll make your product. Actually, I've lost a carbon, didn't I? Whoops. Why did nobody tell me? Ta-da! 3 carbons. Yes. Alright, so pretty standard process. So if on your exam on Monday you are doing a Wittig reaction, if it's in the part where it's like just do the, reactants and products kind of thing, like where it's just the one box, go ahead and use the Wittig already made. If it's a mechanism, though, I want you to show how you make the reagent as well. Okay, or if it's in synthesis, you can also just say I'm using this reagent, unless I say so. So I'll write that down here. So if it's a kind of predict the product or reactant or reagent, no mechanism necessary. So you can just use it already made. If it's a predict the product reactant reagent. The others, you may have to make it. And in fact, I would say, especially if it's a mechanism question, yes, you'll definitely need to show this. If it's a synthesis one, you'll probably want to show it as well, because you're adding carbons on. So generally, you do show that. What other types do we have? Naming, no. No, we're good. So, yeah. If it's predict the product reagent, just say, aha. Whatever it is. So let's say we are starting at, we'll use an aldehyde for once. If it's like this type of one, where we now end up with I don't know, some weird thing like that. Go ahead and use your Wittig. I don't need you to show me how to make it. Just say, aha, step 1. We're going to put in P whatever. Ta-da! That's all you've got to do. Okay, so for that sort of thing, go right ahead. However, if I'm asking a mechanism, then yeah, you're going to have to show the formation of the Wittig. Alright. Does that make it clear?
Yes.
Cool. So, yeah, there we have it then. How would we make this one, by the way? Pretty simple. If we wanted to make it, it's just... Wow, that's ugly. Boom, 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 boom. So notice we have 5 carbons there. So we are going to need 5 carbons. Your triphenylphosphine makes the double bond right where your alkyl halide is. So just replace... Here, I'll show you in one magic step. Oh, I can't. Maybe I can. No, I can. Awesome. How do you know what to start with? Boom. Oh. Ta-da. That's what you start with. Triphenylphosphine and butyl lithium, and you're good. So, making these not terribly hard. It's usually pretty easy to tell when you have a Wittig reaction happening, because you have no oxygen anymore, and you suddenly have a double bond to carbon. Generally, these are pretty obvious to spot out because of that, right? A lot of these other things we had nitrogens or oxygens or other heteroatoms. This is just carbon right here. So, though of course if we have the HWE, you have your ester in there, but generally speaking, these are pretty easy to spot. So, but I know that y'all are going to be practicing this with Charmros, so we'll have fun with that. All right. Any question on Wittigs or HWEs? We'll do one problem. Okay, here we go. What are we going to make out of this? Well, we know how this reaction works, right? We know that in this reaction we are going to basically swap the circled bits. So we just have to decide for ourselves, which side it's going to go onto. Are we going to end up with or this one? So it's just 3 carbons, right? So those 3 carbons are here. 1, 2, 3. 1, 2, 3, or whichever side it went on to. So that's the difference. We're adding 3 carbons. So in order to make the determination of which one's the major product, we have to look at our Wittig reagent, right? We have to say, well, is this stabilized? Is this a stabilized Wittig?
No.
No, it's not, right? There's no electron withdrawing group. There's nothing like that. So that means we're going to get this guy. If it's not stabilized, you're going to end up with your bulky things cis to each other. You're going to end up with your Z-alkene. If it's stabilized, you get the E, which is the second product there. So that's going to be our major product. We will probably still get both, but it'll be like 85-15 or something. So generally speaking, it overwhelmingly predominates as the Z-alkene here. And that's just kinetics. So, because it's kinetically faster to do it that way. So, all right. So that's all of Wittig is. So, in terms of we have one more reaction to cover, and then we'll talk about synthesis. Let's do this one real quick. Is that how we spell? Oh god, I don't know how to spell. It's not villager, but it's villager, and I want to say I'm spelling this wrong. Check the spelling. Okay, one of y'all will do that. Baeyer-Villager reaction, pretty simple. Our dear friend
Instead of the A, it's an I for Villager.
Really? That's it? I swear there was like an extra E in there somewhere. Oh, interesting. Okay. And that's it? That's all I was off on? Okay, cool. Simple, fairly simple reaction. What it does is it just throws an oxygen into your molecule. We don't need to worry about a mechanism for this one. So all that's going to happen is, boom, we throw an oxygen in there. So an oxygen gets inserted into the molecule. And with this one, so basically you're taking a ketone making an ester, or you're taking an aldehyde and going to a carboxylic acid. I want to talk real quick about what to do with this. So if R is H, you always get a carboxylic acid. For example, if you have an aldehyde and try and do this reaction, you will just get the carboxylic acid out. Which you don't need a peroxy acid to do. You can use really so many oxidizing agents to get that to happen. Right? It's an oxidizing agent. Aldehydes turn into carboxylic acids if you're not careful, right? We saw we had to use gentle oxidation to even make aldehydes, so to try and oxidize, if you throw another oxidizing agent at it, it's just going to go to the carboxylic acid. But if we're looking at a ketone, though, we're going to see that we have choices to make. Let me fix that. We're going to see that what's going to happen predominantly is that we're going to get it on the other side. What do I mean by the other side? Generally speaking, you're going to insert the oxygen ideally next to the tertiary. Secondary is about the same as phenyl. So generally you're going to insert the oxygen next to a tertiary one or a secondary, like we're going to follow this order. So here we had a secondary and a tertiary carbon, so we're going to insert it next to the tertiary one. So, because you have to decide which side is the oxygen going to go on, and typically the oxygen is going to go to the more substituted side. So phenyl and secondary are about the same, and then these other ones go less and less. Of course, obviously we just did this, but if you have a hydrogen, yeah, you're going to insert the O next to the hydrogen and make a carboxylic acid. But that would be an aldehyde, right? All these would be ketones. So aldehydes will just go straight to the carboxylic acid. If you have ketones, you want to move your oxygen closer to your more substituted carbon. All right, and if they're equal, then you'll just get a mixture. So I'm not going to do that to you. All right, you're not going to go and look for points of difference. You just look at the alpha carbon right there and say, aha, this is the better one. All right, pretty straightforward. Let's see if I've got some examples in the back here. It's a pretty boring reaction. It's not boring, but yeah, it's kind of boring. Okay. In this case, it doesn't matter which side we put it on because we're going to get the same product. If we do this, we're going to just insert an oxygen. And actually, let me make this a 5-membered ring. I love that I can do that. Okay, 5-membered ring. Now we have a 6-membered ring. Very exciting. So we've inserted an oxygen. Ta-da! So again, either side, it doesn't matter. You end up with the same product because symmetry, right? We can just flip this thing around and we have the same product. So doesn't really matter either side. If we did have another carbon, say something like this, then we would still have that methyl group still there. So this works with cyclic ones as well. Just moves, it breaks this bond here and inserts an oxygen in between those two carbons. So between those two carbons, an oxygen gets inserted. Everything that's on the carbons still stays the same way. And if we were to have some chirality here, it would stay as well. Alright, so it's a pretty standard reaction, pretty straightforward. You just insert an oxygen into your ketone, and you'll end up just kind of sandwiching it in there, and it'll go towards your more substituted side in your molecule. Alright, and you make an ester. In this case, this is a special thing. This is a cyclic ester, which is technically called a lactone, just so you know. These are very important. Many antibiotics are lactones, or actually lactams. But lactones are very useful for us. But in OChem, we don't really talk about them very much, but they're biologically very useful. So those are our lactones. These are just plain old ester. Ketones will go to esters. Cyclic ketones go to lactones, I suppose. And then aldehydes go to carboxylic acids. So there we have it.
Can you scroll up so I see where you wrote the ketone ester?
Of course.
Oh, okay.
Yes.
Oh, got it. Thank you.
Cool. So, aldehyde carboxylic acid, ketone to ester, cyclic ketone to cyclic ester, or a lactone as it's called. All right. There we have it. So that is the end of chapter
18.
18, thank you. Numbers are arbitrary, right? So this is everything that will be on your exam next week. So up to this point. All right, so let's talk a little bit about kind of synthetic techniques here. And then we'll start talking about amines. All right, so tips for synthesis. We have right now did we do 3 different or 4? Go ahead.
Oh, so the synthesis stuff is like something new that won't be on the exam.
No, it's not new. It's just the same stuff. Just kind of just showing, okay, like we've just done the Wittig reagent or Wittig reaction. We've talked about attacking an aldehyde with a Grignard reagent. Just kind of it's same material, but just organizing it in your brain. So it's not new material. None of this is new. So totally still on your exam, but not like it's not new material. So when we start amines, that's new stuff. So new stuff will not be, this stuff just kind of tips for you.
Okay, thank you.
Okay, so we have a couple new carbon-carbon bond forming reactions here. These are the big ones, right? Because, previously in changing the number of carbons, we've had the Grignard, and that's basically it, right? I don't know, did we have anything else? I don't think so. So we have now we can now add a Grignard to an aldehyde or ketone. Let's make those a little bit better. That's kind of new. we have adding a cyanide to aldehyde and ketones. These are kind of new. And now we have the Wittig reaction. This is our newest one. So these are kind of new ways for us for forming new carbon-carbon bonds. And let's take a look at some of these things here, because there's so much we can do with these aldehydes. And so we kind of just want to consider when we're looking at what's happening in a synthesis problem, these reactions can be useful tools for us. And just important to note that the first two will still leave an OH on your molecule. The Wittig will not. The Wittig does not leave any oxygen there. So when we're looking at changes that might happen, so say we are going from, okay, I've got some here. Let's see what we can do with these. Let's see what's happening. Let's see what we can do with this. What can we do to get this to happen? Let's look at this. What's different in these two molecules? Hopefully it's really obvious.
Double bond.
The double bond. And there's a new carbon, right? We have a new carbon here, and it's in green. It's got some H's on it, but who cares? And that looks like a water now. We've added a new carbon, right? So we want to consider all the ways we can add carbon to things. And two of these would leave us with an OH, which is okay, because we can do things with that. We're going to see that we could use two of these different ones to get this product. Although it is unlikely for one of them to. But we'll go from there. So we have multiple bits here. So we've added a carbon. We've added one carbon, and it's double bonded, right? So we're increasing the number of carbons, so we better be having some reaction that does that. So we have a couple ways to do this. If we wanted to take a look at using a Grignard reagent, we totally could. And so we would need if we wanted to put a Grignard reagent on this, actually, we can't. Oh no, but we could. Yeah, we could. We would need this thing, right? If we were to do this, we would first we would make an alcohol, right? And then we would have to get rid of it. How would we get rid of that if we had it? Let's take this a step back. So if we had Grignard reagent would give us this product, right? We would end up breaking we would need to do a H3O plus, by the way, at the end. We would end up with the alcohol and our product here. How might we get that to turn into this? So starting from this ketone, use a Grignard reagent to add your extra carbon. Once you do that, you're left with an alcohol. How might we get this to form? How do we turn an alcohol into a double bond carbon? Go ahead, Eric.
I was gonna say, are we starting from the one on the bottom, or?
I'm just showing you, so with these potential ways to add carbons to molecules, you would need to start from this, right? If you were to use a Grignard reagent to make this product, by adding a carbon there, you need to start at a ketone. Because if you just try to do it from, like, say, a bromine or something, you'll have nowhere to really make your double bond from. So, since also we're studying aldehydes and ketones, probably a good idea to have one of those somewhere in the molecule. So, I want us to focus on just this last step here. How do we go from this thing to this thing?
Protonated?
If we did that, we would end up with this thing. Oh, that's just so ugly. We would probably get that. How do we get the... This is Zaitsev, right? How do we get the Hoffman product? You're right that we want to kind of eliminate that oxygen, but just using sulfuric acid doing an E1 type reaction, we would end up with a Zaitsev product there. Get 4 substitutes on that, but we don't want that.
Well, just instead of a H2SO4, we just add like an acid instead. Or, I'm sorry, a base instead.
If you add a base, you're not going to eliminate it because OH is a pretty terrible leaving
Oh,
group.
right.
How do we make OH not a terrible leaving group? How do you make OH not a terrible leaving group? How do you make it a good leaving group? Besides protonating it. Begins with a T. Ends with oscillate.
Tosylate.
Wow, very good. Yes, if we tosylate this thing, remember that we can do an E2 reaction to get us the Hoffman product, right? If we want the less substituted alkene, we can do an E2 reaction. Put some giant, gross, bulky base, whatever, all these craziness in there. Giant, bulky base will give you the Hoffman product. So if you tosylate this, actually the pyridine is not a good enough base for this. Then you'd need, say, triethylamine. You'll end up getting this to work. So by tosylating it, you get your alcohol to be a leaving group. Then you use a bulky base, you end up getting the Hoffman product, the less substituted alkene. So you could use a Grignard reagent to do this. A little bit easier, though, to use a different reaction, right? If we want a double bonded carbon, well, that screams Wittig, right? If you just put this with a Wittig, you'll get there in 1 step, versus 4 steps with the Grignard reagent. However, either one would work. You're not wrong. Both of these will work. So I think it's probably easier to use the Wittig in this case. because we have a double bond. That's usually a pretty good indicator. So, how do we get now to this ketone? How are we going to get there? How do we get to a ketone from this just plain old alkane? What's the only thing we can do with alkanes? There's only one reaction of alkanes. Come on.
Was it in the last chapter?
Oh my god. This is like chapter 5 or something. I don't actually know the number. It's probably the first reaction you learned in OChem. The only thing you can do with an alkane...
Halogenation?
Halogenation, right. If you just put a bromine on this thing, now we can actually do stuff with it. Wow. Okay. I'm too fast. There we go. If you just brominate this thing, we can get it to have something we can work with. Right? You can't... I mean, alkanes are boring. You can't work with them otherwise. Gotta halogenate them. So, great. We have a halogenated bromine. Remember, that always goes to the tertiary position over secondary, and never primary. How do we go from this bromine to the ketone? Not in one step, mind you. How do we make ketones in general? Only one way to really make a ketone. Oh, just delete half your molecule. Ta-da. Well, there's a couple ways, right? Ozonolysis, oxidative cleavage, those are probably less likely because that means we already have to have carbons there. So let's not worry about that. Oxidizing an alcohol, though, will get us a ketone. How do we go from a bromine on the tertiary carbon to an alcohol 1 carbon away? Not in one step. Still 2 steps in between here. Alright, what's the one thing we can do with whoops. What can we do with alkyl halides? There's really 2 things we can do. We can substitute something or we can eliminate something, right? Those are kind of our choices. Remember that substituting something usually means it's going to be on the same position, or it's going to be, you're going to make a carbocation that's going to go to the most stable position. In either case, substituting this bromine is going to end up putting something right where it is. Right? So if we just put NaOH with this, we're going to get our OH on the wrong carbon. It's going to be on that tertiary carbon. If you try to do an SN1 reaction. SN2 wouldn't work because it's tertiary. So if we can't substitute...
We can eliminate and make a double bond?
Yeah, right. Because we know how to make alcohols from double bonds. Let's do it in elimination. if we eliminate either E1 or E2, either way, actually no, has to be E1, because otherwise we'll get the wrong product. We want the more substituted one, right? So that'll be through E1. So say we're using lots of heat, sodium methoxide, methanol, something like that. Get your elimination product. How do we now get an alcohol on there? I feel like we did this at the end of the, or before the last exam as well. This nice lull of forgetting everything from OChem 1.
You do oxymercuration demigration.
Almost. That one gives you Markovnikov, right? So that would put our oxygen on the wrong carbon. How do we do anti-Markovnikov?
Hydroboration.
Yeah, that's the one. So, what do we have? Hydroboration. We have the, I believe those are the reagents for this. Ta-da, you get your anti-Markovnikov alcohol, which now you can oxidize, which now you can do your Wittig and poof, you're done. So, or if you really wanted, yeah, go ahead, go crazy, oxidize here, and then do your Grignard in 4 steps, and then get your other one. So, yes. Let me make it vertical here. So, all this work just to add 1 carbon. So, I think the better synthesis pathway will be the Wittig there, but you can of course do the Grignard should you be so inclined. There are other ways to do this, of course, but it should be noted that because your exam is on only 2 chapters, right? It's on aromatic reactions and aldehydes ketones. You got to at least have something with an aldehyde ketone or aromatic in this. So try not to just use only OChem 1 reactions with this. So we're using a Wittig here. We're using a Grignard onto a ketone. Those are both newish things. So that's another hint for you. So generally speaking, all of these should have some way to get them done using either an aromatic reaction, not applicable in this case because we don't have any aromatics. So obviously we have to use an aldehyde or ketone here. So that's our hint. All right, let's do another one. All right. How about this one? Any questions on that one, by the way? And just for fun, let's go ahead and... There we go. Let's put both at once, and let's get rid of this pesky line. Well. What have we here? We got multiple things going on this. We have added two groups, right? We have group 1, group 2. Two things we've added to this benzene. Again, I think a good thing to do is to figure out how to put these on. How do we put the green thing on?
Regular hydro.
Halogenation.
Halogenation.
Right. Bromine and a Lewis acid will get you that. How do we get the blue thing?
You could do Friedel-Crafts acylation and then modify it.
Yes, indeed, I like it.
I was gonna ask, can alkylation work too, or?
Yes. But we have problems. Alkylation would be like 5 more steps. The reason being, your alkylation product is an orthopara director. Bromine is also an orthopara director. So these are meta to each other. You're going to have to do all sorts of other things to get these to both be meta. You're going to have to, we don't even have the tools yet to do that. And then, yes, you could then stick on a pentane or something, do an NBS and an elimination that way. Yes, you would end up with the product. But let's not worry about that. That's too many steps, and it's a lot easier to use an aldehyde or a ketone here. So Friedel-Crafts gives you a ketone, right? And then we can modify it, right? I like that. Which one are we going to do first? So we notice these are meta to each other. How are we going to get them to end up meta to each other?
They're both orthopara, right?
Those are both currently orthopara directors, yes.
Mm.
But what's the product of the Friedel-Crafts reaction? It's a ketone, right? What type of director is a ketone?
Meta.
It's a meta director, right? So that's a hint. That's probably what we should do first, right? Because we need these to be meta to each other. So first thing first, we can go ahead and say, that's right. Let's do that. Let's do a Friedel-Crafts reaction. Remember, Friedel-Crafts gives us a ketone, which is a meta director. All right, so what do we want to have as our R then?
Methyl group.
A methyl group. All right. So if we do this, we'll end up getting our product, right? Friedel-Crafts acylation. Now what? Well, we know before we modify it, if we modify it, it turns into orthopara, so we should probably put that bromine on next, right? While we still have a meta director. So, probably a good idea. Let's go ahead and do that. Ooh, that's ugly. There we go. All right. Switching to this view. Now what?
Wouldn't we need to add a ethyl group first,
I
or
think
no?
that would be a better idea. Yes, because indeed we have... Actually... Yes, we want 3 carbons on this thing. So it should indeed be an ethyl group there. Yep. I was waiting for someone to notice that. Alright, so what next? What type of modifying are we going to do?
Wittig?
Say it again?
Wittig?
A Wittig reaction indeed would be a good idea. If we did that, what's our Wittig reagent?
Just a methyl.
This guy? Oops. Yay, we did it. Oh, wait. What?
I see the
I see the problem too. What is the problem, Eric?
It's
Yeah,
it's
it's a Z alkene, right? That's technically the phenyl group, right? We have to do a Wittig reaction like this. We're gonna end up with a Z alkene, bulkier things close
so
to
we
each other.
use
So that's a problem, right? So that tells us Wittig not doable. No Wittig allowed. What do we do? I'll give you a hint.
I was gonna say the
Uh-huh.
Horner Wadsworth.
Ooh,
Hamilton,
well,
I realized.
so the problem with
Yeah.
those, I mean, yes, that would fix the geometry problem, but in our product we don't have these, we don't have an ester, we don't have the other bits there, right? So nice try.
Can we add something that stabilizes it?
Unfortunately, I mean, yes and no. Things that would stabilize it would be an electron withdrawing group. You would need to have, say, a nitro group here, and then, or whatever, and then, you know, that would help. But we don't have that. In our Wittig, we just don't have that. We only have a methyl group. So there's no way for us to add an electron withdrawing substituent. So that's a hint. Wittig is not an option here.
Clemenson wouldn't work either, would it?
Clemenson would just get rid of our double bond.
Right.
Oxygen.
Just how many more steps until we get to final
Like
product?
3.
3 more.
Well, let's look. Ways to form carbon-carbon bonds. Wittig is out. There's 2 other ones right there. Choose one. Grignard, what a great idea. Alright, what Grignard do we want to do?
CH2 MgBr.
CH2 MgBr, wow. We have a carbene Grignard. That's an interesting choice. I would say probably not a good idea for several reasons. First off, I think you're thinking CH3 MgBr. Second off, how many carbons are we adding on here? How many carbons do we need to put on?
two.
Right.
Oh, I
yeah,
see.
we're
Okay.
missing 2 carbons here. So, probably a good idea would be to put 2 carbons on. So, let's use an ethyl Grignard reagent. That would give us this is doohickey. Now what do we do?
We could protonate.
I like it. Eliminate. No matter which way you eliminate, you get the product. So, ta-da. And that's all you need to do. So I lied. It was 2 steps, Eric. No. Boom. It is indeed 3 steps. So, hooray. Alright, so these are the considerations we need to make. Adding carbons to molecules. Grignard and Friedel-Crafts. Well, Friedel-Crafts adds carbons, but Grignard and Wittig are our 2 main options here. Wittig works for Z-alkenes. If you have an E-alkene, chances are you're going to need to use a Grignard reagent, unless you have some way of stabilizing. If on your molecule you have already some stabilizing component that you need, for example, that's weird. Oh, that's a fun one. If you had a stabilizing component like an ester on your target compound, then you can make your E-alkene using a stabilized Wittig, right? But you just need to make sure that you have that in your product, because if you don't have an ester in your product, can't really throw an ester in there for no reason. So, although I suppose you could, but then that's a lot more steps to deal with. You'd have to hydrolyze your ester, and no, we don't know ways to get rid of carboxylic acids yet, so never mind. There we go. Forget it. So you can't just throw in ester for no reason. So if you have an ester in your product, that's fine. Go ahead, use your Horner-Rogers-Lemons. If you don't, tough luck. So let's see. Do we have any other examples here where we might do that? Any questions on that one, by the way, while I look at some potential problems for us? These are all terrible problems. None of these these are all Z-alkenes. Okay, well, there we have it. Yeah, all terrible problems. So, oh. Any questions on that one? Practice, practice, practice. This one we used reactions from both chapters, right? We did aromatic reactions. We did some ketone stuff. So there are a lot of reactions. There's a lot to keep in mind. Mostly, though, the mechanisms for these are pretty much all the same. All the stuff for aldehydes and ketones, there's really only 2 things. You have a base catalyzed process and an acid catalyzed process, and they're really similar. And no matter what you're putting on to your aldehyde or ketone, really goes through the same steps, right? You protonate, then you attack, then deprotonate, then move the proton around, and and then do it again. For aromatics, you really have electrophilic aromatic substitution, nucleophilic aromatic substitution, and then elimination addition. You have 3 mechanisms there. And so mechanistically, this is not a tough set of chapters because the mechanisms are so similar to each other. And so the hard part here is all of these different reactions and all of these things to think about in terms of regiochemistry. So whether something is an orthopara or meta-director, whether something is going to give you an E product versus a Z product, or if there's other stereochemical concerns. Lots to think about here. So, yes, it's fun. Yikes. All right. So you'll do more practice. And yeah, we'll go from there. So I do have office hours today later on. So if you want to do some more or something, we can do that. Okay, so alrighty. Same format as...
We're gonna have office
Wait,
hours.
go ahead.
Oh. I was gonna have office hours at 12:30 or
12:15,
12:15.
normal time. So, okay. Alrighty. We're going to talk very briefly about amines since we got 10 minutes. All we will do is naming them. This stuff is not new. Or, no, this stuff is new. So, not on exam. Alright, amines. Well. Alright. This is called ammonia. You know this. You have smelled it. Maybe you haven't. I don't know. Was 102 in person for you guys? I don't think so. So maybe you haven't. You used a lot of it in 102. So I guess you did that virtually. Whatever. This is a primary amine, secondary amine, tertiary amine, and a quaternary ammonium. These are amines, these 3. So carbons, we talked about how many carbons were on them, right? We do the same thing with amines. So primary amine has 1 carbon on it. A secondary amine has 2 carbons on it, and a tertiary amine has 3 carbons. A quaternary ammonium has 4 carbons on it. And then ammonia, of course, has none. So these are our kind of like basic ones. Amines are, thankfully, never going to be a priority group. So they are kind of same priority as alkanes. So amines do not have priority over any functional group. Meaning that typically we're going to see these as prefixes. So the prefix name is amino, and the suffix name, which is rare, is amine. So thankfully they're very similar, right? You will only see the suffix name in very simple amines only. Like, for example, triethylamine. Something very simple. You'll see the amine name there. Typically, though, because amines are part of more complex things, you'll usually see these as amino groups rather than as amines. So yeah, you can say something like this. You could say for example, ethyl methyl propylamine. This would be a common name. It's not an IUPAC name. But simple amines, you might see them written like this. However, very often, you'll have, something like this. Some normal compound where you have an amine just sticking on there. And how we're going to name these is, it'll be amino, but any substituents they don't get a number. They get N. And we'll take a look at what that means. So, if we were thinking about naming this compound, what we would normally do, find our longest chain that has our higher priority group. We don't have any high priority groups in this molecule. So, let's see how we're going to name this. So, we could choose the top numbers or the bottom numbers. We always want to choose the ones that give us the most substituents with the lowest numbers. So that's going to be the top set of numbers, right? So I'm going to erase these bottom ones because we're going to get 3 on bromo and then 4 on the amine. Okay, that was a little too much. We're going to see that on carbon 3 and 3 we have a dibromo. On carbon 4 we have amino. On the nitrogen we have an ethyl. That's how we name it. So we don't have to use the parentheses here. We just say, well, on this nitrogen there's an ethyl group. Boom, done. N-ethyl. And the N, just like we pretend it's a number. So we're not going to say the N doesn't count for alphabetical, so we're going to still have amino, then bromo, then ethyl. So I guess it doesn't make a difference in this case, and it'll still be hexane as our parent name. We do have one little bit of stereochemistry to do here. So this will be highest priority 2 and 3, so this is an S stereocenter. So we're going to have to say S, or rather 4S, 4 amino, 3 dibromo, N-ethyl, hexane. So the only new things here are amino group and what to do when you have substituents on your amino group. So in this case we had an ethyl group on our amine, so we say anything that's not hydrogen we're going to write out, whatever it is. If we had something like this, it's not chiral, so who cares? So we'll say for this one it'll be 2 what is that? 4 MN tetra methyl 1, 2, 3, 4, 5 pentane. Oh, I forgot the amino. Shame on me. Why did nobody say that? Oh wait, that stays there. What am I doing? Alright, let's move the whole thing down. I got ahead of myself. So 3 amino, 2,4-NN tetramethylpentane. So just like before, you would group up all your things, whether they're on the nitrogen or on the carbons. You use numbers if they're on carbons, you use N's if they're on nitrogens. And so then you'll do that. Technically, if you have multiple amines, which is not something I'm going to give you. You have to specify which N it's on, but that's not something we're going to see here, so we're okay with that. We're not going to have anything more complex than something like this with a couple more substituents on it. So, all right, so that's how we name amines. And those are our types of amines. So, all right, I guess that's all we have time for. So I'm not going to start talking about how to make amines. So, all right. Yeah, go ahead.
So you said so it's N whenever it's an on the nitrogen and.
So with this particular one, we have on the nitrogen, it's a methyl group, and two more methyl groups on carbons. So that's why we have methyl on carbon 2, methyl on carbon 4, methyl on N, and a second methyl on N. Altogether 4 methyl groups there.
Okay.
All right.
Okay. Thank you.
Mm-hmm.
Thank you.
Alrighty, well that's it for today. So have fun, study well. Probably see you at office hours. If you'll, yeah, we'll see. So we'll come to office hours. We'll continue with the meetings on Wednesday, and we'll go from there. All right. So have a nice day. Go ahead. Of course.